So today we're going to be talking about velocity and acceleration. The position of an object can be expressed as a function, s equals f of t, where s is the displacement, a directed distance of an object from the origin at time t. Using the definition of the derivative as the slope of the tangent, the derivative of a displacement function is the velocity of that object at time t. So let's draw a quick graph. So this is a displacement graph. We've got time across the bottom, displacement across the side, and we have an object that starts at the origin, moves away from the origin, and then returns to the origin. The velocity of this object can be recorded in one of two ways. We could either talk about the average velocity between 2 points. So this is just the slope between 2 points. Or we could talk about the instantaneous velocity, which is the tangent at any point. So if we were to take we find the tangent here, we would be finding the instantaneous velocity. Okay, so let's look at an example. So let's say that the position of a particle, s of t, is given by the equation s of t is equal to 2 times t cubed minus 5t. The first question asks us to find the position, that's s of t, of the particle after 3 seconds. This is my t. So it's asking for the position, so I'm going to use the position function and put 3 into the t spot. 2 times 27 minus 15 is 39. The next question is asking for the velocity of the particle at t seconds. Well, the velocity I can determine by finding the slope of the tangent at that point. So I'm going to find, so the derivative of the displacement function is the velocity function. So I'm going to go ahead and take the derivative of my function. 2 times 3 is 6t minus 5. And there's my velocity function. The next question is asking me to calculate the velocity of the particle at 3 seconds. So I'm going to take my new representation, my new function, and put 3 in there. Oops, I need a squared there. 3 squared is 9 times 6 is 54 minus 5 is 49. Let's try another question. So the height of an object that is thrown into the air is given by the equation height of t equals negative 4.9 t squared plus 13.72. Question 1. Determine the height, the maximum height of the object. I'm just going to draw a quick graph just so we can kind of see what's happening here. So you have an object, it's thrown up and comes back down. And the question is asking me to find this maximum height, this height right here. And that's going to happen at a very particular point of the graph. That's going to happen when the object changes direction. When the object changes direction, the velocity is going to be 0. So in order to solve this, I am going to take the derivative of the height function to find the velocity function. So negative 4.9 times 2 is negative 9.8 t plus 13.72. So when the velocity is 0, I want to know when that is. So what is this t value here? So I'm going to set this equal to 0. And rearrange to solve for t. (13.72) divided by 9.8 is 1.4. And so now I know that that's the value, the time, specifically, of when the velocity is 0, which means the particle or the object has changed directions. That doesn't answer my question, though, because my question was looking for this height. So I want to know what is the height at 1.4 seconds. So I'm going to take my height function again, And I'm going to put this time right into it. Okay, put that in my calculator. Negative 4.9 times 1.4 squared plus 13.72 times 1.4 is going to give me 9.60, and let's give it a unit of meters. So there's my final answer. At what time will the object hit the ground? Well, the object will hit the ground twice. Here and here will be at the ground twice. And the hitting the ground is a function of the height. So I'm going to use the height function. So my height function is negative 4.9t squared plus 13.72t. And I want to know, when is that 0? When is it at the ground? When is there no height? So I'm going to common factor out this t. And now I'm going to find the two cases. So here's my first case here. When t is 0, the height is 0, and I know that that's my first point there. And I'm going to look for the second point there, when this part is equal to 0. So when this is 0, then that's my other case. Negative 4.9t plus 13.72 equals 0. Rearrange to solve. 13.72 divided by 4.9, t equals 2.8. And if we look at the graph, that makes sense that 2.8 is there because the function is symmetrical and the vertex was at 1.4. So it does make sense that 2.8 is the distance to which that, or the time at which it will hit the ground. Okay, last question. I want to know, what is the speed at which the object hits the ground? Well, speed is another word for velocity. So this is a velocity question. So I'm going to use my velocity function. And my velocity function is negative 9.8t plus 13.72. And I know the time that it hits the ground, so I'm going to go ahead and plug that in. And put that into my calculator, and I'm getting negative 13.7 meters per second. Makes sense that it's a negative because it is on its way down. Okay, related to these problems is page 124, numbers 1 through 5, and then also 7. Before you get started on that, though, I just want to quickly talk about acceleration. So the acceleration of an object is the rate of change of the velocity with respect to time of the object. So in other words, it's the derivative of the velocity function. So in order to find the velocity function, we took the derivative of the displacement function. And in order to find the acceleration function, we're going to take the derivative of the velocity function. Or in other words, we just take the second derivative of the displacement function. And to practice these ideas, taking the second derivative and applying it to a scenario, you complete page 129, numbers 1 through 3 and 7.